indirect objective functions, and the envelope theorem. Economic problems generally involve choice variables that are under the control of a person or a firm, such as how much good to buy or produce. Economic problems may also depend on exogenous parameters that influence the decision maker's behavior but are not under the decision maker's direct control, such as the price at which the good can be bought or sold. We can add these exogenous parameters to the formulation of a maximization problem. To illustrate this approach, we examine a function g colon open bracket 0 comma 1 close bracket times open bracket 0 comma 1 close bracket times capital R yields all real numbers. We write this function and its arguments as g of x sub 1, x sub 2, and z, where the variables x sub 1 and x sub 2 are choice variables and z is an exogenous parameter. We assume that g is continuously differentiable in all three of its arguments and is strictly concave in the first two, the choice variables. Consequently, g has a unique global maximum even if g is not concave in the exogenous parameters. The decision maker's problem of choosing x sub 1 and x sub 2 to maximize g given z is written as we're taking the max of a function with respect to x sub 1 and x sub 2, the function max g of x sub 1, x sub 2, and z. The first order conditions are partial derivative of g of x sub 1, x sub 2, and z with respect to x sub 1 equals 0. The partial derivative of g of x sub 1, x sub 2, and z with respect to x sub 2 equals 0. So the optimal choice of x sub 1 and x sub 2 typically depends on the value of z. Accordingly, the values of x sub 1 and x sub 2 that solve the optimization problem for a given z may be written as x sub 1 star of z and x sub 2 star of z. Given a solution to the maximization problem, the value of g at the maximum is g of x sub 1 star of z, x sub 2 star of z, and z. Given some value z, the act of maximization determines the optimal values of x sub 1 star and x sub 2 star. Accordingly, we may sometimes write the maximum as capital V of z equals g of x sub 1 star of z, x sub 2 star of z, and z equals the max of g of x sub 1, x sub 2, and x sub and z, and that's the max of x sub 1 and x sub 2. The function capital V of z is called the value function because it tells us what the value of z is to the decision maker. It is also called the indirect objective function. In contrast to g of x sub 1, x sub 2, and z, which is the direct objective function. A natural question to ask is how the value function changes when z changes. At first glance, this problem is very complicated because, as we have seen, a change in z has a direct effect on the value of g of x sub 1, x sub 2, and z. And it also causes the decision maker to change x sub 1 and x sub 2 in ways that may be complicated. However, at least for small changes in z, an important shortcut to solving this problem exists. The envelope theorem tells us that the direct effect of small changes in z matter, but that the indirect effects do not. That is, according to the envelope theorem, the solution to our particular problem is the partial derivative of v of z with respect to z is equal to the partial derivative of g of x sub 1, x sub 2, and z with respect to z, equation capital A dot 5. We offer another more general statement of this theorem below when we discuss the solutions to constrained maximization problems and offer a constructive proof.